or Neil, and all for those who have been listening, talking machines. So in the last episode, Neil is talking about licensed Bayesian, and I thought to add that to my title. So in this talk, there's two parts: GP hyperparameter inference, a lot about priors on GP hyperparameters, benefits of integration versus point estimate, and MCMC and CCD for making these integrations. And then if there's still time, then a little bit about estimating the predictive performance. So you of course know that the GPs are priors on function space, but most of the time we have then the parametric covariance function, and then we need to think about priors on those parameters. And then if we have big data and small number of hyperparameters, then we know that when the amount of data increases, the posterior of the hyperparameters will concentrate, and eventually there's not much difference between the point estimate and integration. And that's why also in machine learning, where the focus has been a lot to get GPs to scale to big data, then it's been just the maximization of marginal likelihood or lower bound in case of using BB. And this holds even more when these PG type sparse approximations are used, because they limit the complexity of the models, and then there's even more data kind of affecting the posterior of the hyperparameters and making them concentrated faster. But then Javier showed good examples of small data cases, like Bayesian optimization, where we might have really costly function estimates, and then we want to find the minimum or maximum of function with least number of possible observations. I will soon show you this notebook, which was made by Michael Betancourt, and I made some adjustments for this talk for that. But here there are some observations. Hopefully you can see also in the back. And the question would be, for example, if this would be a Bayesian optimization, where's now the maximum of the function? And if we are not careful and fit GP, we could get something like this. And I've seen this happen in real Bayesian optimization applications. And you can see now the uncertainty is such that it's saying that, okay, almost everywhere between the points there's the same uncertainty, and we are not very wise about where the maximum could be. And then there's two things in these small data cases how we can improve are then priors and integration. Go to the demo. And my goal was before coming here was to have this notebook all with GPy. But unfortunately, GPy is not yet fully Bayesian, can't do everything I want. And so I'm demoing first with Stan, and then I will discuss what is missing from GPy currently. Some of those things are already implemented, but on branches which are not yet merged to develop or master branch, and some of the things are going to be soon to be added. So we have here the same data I had there on the slide. And it's still kind of the unclear what the function might look like. I will show now also then the actual whole data, which gives you much more impression of now it would be, with the big data, it would be easy to think how the function would look like, but specific realization may look quite different or much more different to figure out. And then the first example is then that what if we don't have any priors and we just optimize. And it seems that quite many Bayesian optimization software using GPs are doing this. And I guess that in quite many papers making comparisons between different methods, part of the results are garbage because not doing this sensibly. Even so that in some paper they showed that random search worked almost as well or better as Bayesian optimization. And of course, if your fit is like this, it's practically now random search you are doing if you use this to base where to make the next acquisition. So if you are not careful with the small data case and you use it for Bayesian optimization, it's likely that you are doing just random search. Yes?
Just sort of a clarification question. So the maximum marginal likelihood of fit is learning a length scale, which is really short, I presume.
Yeah, so in this case, so there's the length scale, the signal magnitude, and the noise variance. And they are only constrained to be positive. But now it happened that it could find the solution where the length scale is really short. And in this specific case, these observations were so that they are evenly spaced, which also affects this, what happens here. And so what happens now is that it can then find this solution which goes exactly through the points and makes the noise to be 0. And here are the posterior quantiles for the function, the previous for the realizations, or predictive quantiles, which looks about the same because the noise is practically 0, so it's only about the uncertainty where the function goes. Now we could then think that, okay, let's integrate what then happens, but still no priors. And we use Stan, and oops, it's because it's now showing also the efficiency for the predictions. Let's see if I can scroll in the So now happens something different. This is log length scale, and actually I think these values are more like the length scale values itself, but then it's built in log scale, and these are really large. And now what happened is that on the other, when the and let's see also the what's the prediction look like. It's flat. And what happened was that when we have a flat prior on length scale, so is there a marker? So if our scale of the data is from -10 to 10. And at some point, when the length scale parameter is large enough, our GP is already flat. If we make the length scale larger, it's still flat. Larger, still flat. And it happens that the posterior then has just flat tail, which goes to infinity. So it's for the large values, it's not identifiable anymore. Also with the optimization, sometimes I've seen that it happens then also that it finds the mode where it decides that everything is flat. But now when we look at the posterior distribution, even if the posterior would have a mode somewhere smaller values, the tail is practically uniform. So we should have a prior which says that really large values for length scale are not feasible. So let's use weakly informative prior, sample again, and we get much better results. So this is now the log length scale, and then there was the log magnitude, log length scale, and log noise sigma. Now I'll show you the predictions and then come back to this figure. So here are the predictions, or the draws from the posterior. You can see that there are some of the draws are quite wild. So we were able now with the prior, which said that large values are not feasible, to get away from going flat. But now we are still allowing very small length scales. Integration helps that it's not finding the mode with the very long scale or getting stuck at the mode, but it's also seeing that there's a posterior mass for larger length scales. But we still have this case that with the very small length scales, there's also now the identifiability problem for then the noise variance. We could, in some cases, we might have prior information also about the noise variance, our measurement accuracy. Sometimes the optimization task we have, we know what is the accuracy of these acquisitions. In this specific case, we have that the observations were evenly spaced, if instead of Bayesian optimization we think that it's a time series problem, we know that we are not going to get more observations between these. Let's say these would be like daily observations. We are possibly getting more daily observations, but not between. And then it's reasonable to say that we should not go to length scales which are smaller than the smallest distance. I'll come back to these green dots later more, but they are diagnostics from Stan saying that also that this part of the posterior distribution is really narrow, and it's likely that the Markov chain is not able to explore that part of the space well.
Aki, last question.
Yes?
Is the mode, so the maximum marginal likelihood solution was falling into a mode, was finding the mode, and that presumably was somewhere near that green stuff? Was it more to the left, or?
Let's see if I had a histogram for this. And these are now just for one data realization. And it's also that if we, even if from the same true data generation process, different data realizations could produce different results where the mode is.
Okay, so it's not the same. It's not
And that's why it's also, and I will come also back at some point. There's a certain complication, the difference between the optimization in Stan and in GPy, which is a bit more technical issue, but I'll come back to that.
But maybe for the people who are not experts, you suspect there's a narrow peak in posterior space which the maximum likelihood or the max solution is going to.
Yes.
Big sort of mode which the sampler is exploring there, and the mode's much more sensible
Yes.
than the high density peak which the first thing is.
Yeah. It's also, it's interesting that, so here, so this part is narrow. Optimizer can get easily there. MCMC methods have more difficulties getting in narrow modes. In deep learning, if you would do good optimization, you would get in the narrow modes. And state of the art is then to use large enough step size not to get in these narrow modes and to stay somewhere in a more reasonable region. With Stan, we've observed several model cases where previous MCMC implementations had missed these narrow parts, and that's why there are some that kind of prior recommendations that are not working anymore with HMC and NUTS, because it's able to get also in these more narrow regions. Yeah. Okay. So we were not restricting enough to small values, so it was getting something more reasonable, but still getting also these wide ones. But just by adding for the length scale suitable prior, we'll get nicer posterior distributions, but also nicer realizations. Now you should really look the realizations compared to the training data and not be annoyed by the fact that it's not seeing these data. But as you can see, all the observations here were quite low. So it was just that this specific realization wasn't so well representing the true data generating function. But it's now much more stable. And so it is useful to have priors which restrict or make the too large values less likely, too small values less likely. Sometimes we might have information about the noise variance, measurement accuracy. Of course, then that can be used, and then it would also affect the lens scale posterior. Usually we don't have so much information about the signal magnitude. But it's usual, again, also that it's enough that we have information from at least one of these three parameters, and it helps a lot. And there's the posterior quantiles, posterior predictive quantiles for this. So the summary was that the likelihood for the length scale beyond the data scale is flat because the functions look all the same. If no repeated measurements, we have non-identifiable between signal magnitude and noise magnitude. When length scale short, should have prior for the short length scale, less likely. We have also non-identifiability between length scale and magnitude, and the ratio of them actually is the one we can identify better and which affects how flexible function we have. In machine learning, there hasn't been much interest in looking at the posterior distribution of the length scale. In like the spatial epidemiology or time series, sometimes people might be interested in looking at the length scale, but then it's really difficult to actually interpret that because there's a strong posterior correlation with magnitude. I have a other demo where it's shown, but I can just draw also. So it's just that usually for the, especially for the log length scale, log signal magnitude, let's say alpha, posterior distribution is often looks something like this. With the non-Gaussian likelihoods, Poisson is interesting in that the variance is equal to mean, and then there's no this problem that it could overfit. It can't make the variance of the likelihood go to 0, and there's less danger for that it would go to the short length scales. There's still a problem with the large length scales. Except if the data is not conditionally Poisson distributed. So if it, for example, it has over-dispersion compared to Poisson, then you can overfit. And then you can get the length scale again too short. But of course, you should use such model checking approaches that you can also find that you would need some other distribution. Binary classification, logic probits. The likelihood is unbounded if separable, and in case of GP, so if we have, so there's a class 0, class 1, and we would have observations like this, we get unbounded likelihood if it can fit like this and it can make the length scale short enough. Even if we would have sometimes like this, it could make, then it's just short scale, again short enough that it can visit all the observations. Why this hasn't been an issue in a lot of machine learning literature using GPs for binary classification is probably because using, again, the Fitzy type models which restrict the flexibility of the model so that it can't really go for the short length scale models. But this is something which is more likely to happen with the, like deep neural networks, that they can learn the training data exactly, and then that's why there's these problems with that the adversarial attacks showing an image that human would interpret to be cat, and deep learning model interpret it to be a car. So in binary classification, it also might be that you need to have the prior for not too short length scales. And I already mentioned about these the sparse approximations. So these examples were now with 1D. If we go to higher dimensions, so using GPs in multidimensional Bayesian optimization, or using it for regression, classification, survival analysis with several covariates, it's reasonable to again use priors similar as in this 1D case. And then at that point, I want to also remind you about the interpretation of the length scale. If we have a separate length scale for each dimension, it's often called automatic relevance determination, which is really bad name because it's the length scale is related to nonlinearity and not to the relevance. Here's a toy example illustrating it. The function is just additive function of these 8 terms you can see there. And you can see that there's a variation in nonlinearity of these terms added. And this has been now scaled so that if you drop any one of these inputs, your performance drops the same amount. And this shows that if you drop any of the inputs, this is kind of the true relevance, how much you lose in predictive performance if you remove that. And this how the inverse of the length scale looks like. So with the small length scale, we get high relevance. But now for first components, they are so close to linear that it can use large length scale. And if you would think this as a relevance, you would say that, okay, they are not relevant. This is especially bad in those cases that what if your model is then just y equals x plus some noise. Maybe you have also some parameter alpha there. And then for some reason you don't know this, you measure 2 things. You happen to measure x and x squared. And you fit the model, and you would then choose this one based on ARD value because it's more nonlinear. So don't look at the length scales, don't use the term ARD. So one important message was now that after the Bayesian optimization talk, that overall in the literature they've been used too much as black boxes, and you should use better prior. The bonus would be also that you could use shape-constrained GPs. We have a paper showing how you can add additional information that the minimum is not on the edge. So in some cases we can be quite certain that expert can say that that the minimum is inside this box, but it's not on the edge. And then we can add additional information. Without this additional information, it's quite likely that in Bayesian optimization we do a lot of evaluations on the edges because the variance is there high. Other covariance functions. So this in time series prediction, time series modeling, it's common to use periodic covariance functions. If you know the period, just fix it. You will get problems if you try to estimate something you know. For example, when considering, like I have the birthday example or sales data, we know that there's yearly period, weekly period, and better to fix those. There are problems where we don't know period. One of my students is working with astronomical data, quasars, and then we don't know period for those. But then GPs and periodic covariance functions, you will get possibly serious identifiability issues unless you will use even some other way to first integrate data about the frequency or the period length, and hopefully also some additional prior information about sensible values, and then use informative prior. The demo I showed was using just a plain GP, which is the common also in the Bayesian optimization. But then in this kind of the regression, classification, survival analysis, it's common to center GP on top of linear model, assuming that the function is almost linear, and then there's only some non-linearity, or with respect only some of the parameters, there's non-linearity. Now there's this the large length scale case is even worse when we combine GP with linear model. When it was alone, there was the only problem that when the length scale is so large that you are modeling already with the flat function. But now there's also the range of length scales that it's not yet flat, but it's almost linear. And then the identifiability issue is that are you modeling the linearity with the linear model or with the GP? And if you want to recognize when the GP is needed or not, you should again use a prior which says that, okay, length scale is only allowed to be such that it's clearly nonlinear function, and if it's not needed, then the magnitude term goes to 0. Otherwise, you might get a too large length scale and the magnitude doesn't go to 0, and then you don't know whether you are could drop the GP out.
Sorry?
Yes?
So can you then use ARG with the kernel, with a linear and exponential kernel? Because you said just using ARG with a squared exponential, let's say, is not good because you neglect actually the linear behavior of your system.
Even then, so if you have a linear model, you would restrict the length scale so that GP would model only the nonlinearities. Still looking at the length scale would favor more nonlinear inputs to be added to the model. So it's still the interpretation, it's not good to think about the length scale as relevance. It's good to just that, okay, it's about the nonlinearity. Same for other parametric models plus GP. We need more informative priors. There are papers on when you have some computer simulator, deterministic simulator, you might have idealized physical model from first principles, and you want to use a GP just to measure some deviation from this ideal case and still learn also the parameter for that simulator or the physical system, but you can't learn those if you have an identifiability issue that which part you're learning with the GP and with the parametric model. And there's several papers on that. GP plus GP. So this is an example of bunch of additive GPs combined. So these are number of birds per day from 1969 to 1988 in US, and it has many components. So there's in the top one, blue one, slow trend, and these are years here. There's yearly seasonal effect, so there's more birds in autumn. This is a weekly effect. There's less birds during weekends, and this has the size of the effect has about doubled from this data to data from this century, from 2000 onwards. The effect is about twice the effect shown here, and this is of course because of the so many birds are there's a C-sections, and also the artificially started, so they are planned, and then they are preferred. The doctors like to play golf during the weekends, and then they are planned for the weekdays. Then we have also less birds, New Year, Independence Day, Christmas, and then of course they have to burn at some day, so there's a peak before Christmas and after Christmas. There's a peak before Independence Day, after Independence Day. We can see also drop Labor Day, Halloween, Thanksgiving. It's a very important holiday in US. There's a small drop April 1st, small drop leap day, even if in accounting that leap day is only every 4th, and small spike upwards Valentine's Day. So they are really parents are planning this when to then to have the bird. Okay, a funny story, of course, in the birds, but the main thing was that when I was fitting this model, it was likely that when I started with the kind of the random initialization for the hyperparameters, that different components could end up explaining different things. And to make it more reliable, I really had to add kind of more informative priors, that what kind of length scale I want to have for different of these effects, in a way that I want this to be a really short length scale, and there's still, even if this is a short length scale, there's some identifiability issue here, that some of these bumps happen to match also some of the bumps here, and it's really difficult to get kind of them separated because these happen to be somewhere in the year, and this was also, even if it's the slower trend, to separate those. In a way, there's too many length scale processes going on at the same time. Also, there's no specific model for this, that they have to burn at some day it would probably identify better if they would take into account that if it's not this day, then it has to be higher on other days. Some identifiability issues also with this and this component and so on. And this using GPs is getting more and more popular in, for example, predicting sales, customer flows, and so on. And not necessarily GPs in a covariance function framework. There can be different parameterizations, and also in these dynamic models. Simo probably talked here, but still, if it's kind of the combination of the different levels, you need to think about the priors. This is something which clearly requires more research, that what would be the priors which encourage specialization of these components. In a way, we would like to have a prior which says that the posterior of the length scale should not overlap much. We would like to say that, okay, let this component explain this and this, and they are not allowed to kind of to go explaining same things. So with small data, better to integrate for further stability and for better predictions. So the slides will be made available, and so you have the specific prior recommendations for length scale. You can also find these in Stan manual. Inverse gamma has a sharp left tail that puts negligible mass on small length scales, but the generous right tail, allowing for large length scales, but still reducing non-identifiability for going to really flat ones. If you need to combine GP with a linear model, then it's better to have even sharper tail also on the right-hand side. Generalized inverse Gaussian would be good in that case. And if you have the length scale covered, then currently we are recommending half normals for the signal magnitude and noise magnitude, not on the variance, but the kind of the standard deviation scale. And of course, if you have information on the measurement accuracy, you should use it, and then you can use these gamma or scale inverse key priors. Probably should be inverse gamma. Currently, the problem is now that GPy then doesn't have these priors we recommend. They are already in one branch, and so they will be available at some point. Currently, GPy also, it doesn't allow you to put at the same time constraint to be positive and then normal distribution on top of that, which would produce the half normal because of incompatible supports. And then we need to add specifically these half versions, because then it's good to have then these constraints and then working on the transformed unconstrained space using, for example, the log transformation. GPy has Hamiltonian Monte Carlo, but it doesn't have no U-turn sampling. I'll show you soon why that's much better option for sampling. It doesn't have easy predictions with MCMC samples yet. CCD is also in a branch which is not yet in the master. It would have been, but then Alan asked that it's not merged before this summer school. And then I think that I don't have time to then talk about much about Lee1 out. I'll still talk about MCMC and CCD but then also these leave and out cross validation things are not yet there, but soon. So now I go to demos of Hamiltonian Monte Carlo. Now I think now I probably should see the same here and there. Just a moment, I'll adjust my screen. No. Okay. So I'll try then to oops. Okay, I lost network connection. Had it just recently. Getting IP address and connected. Okay, so this is just the Metropolice random walk. I intentionally chose this donut because when we have strong posterior dependencies, there are these narrow paths which continue a long time. Of course, the donut itself is not so likely, but these kind of correlated things are. You can see the red arrow is then when it's rejecting, and because it's a narrow, it's rejecting a lot. And of course, we could make then the step size smaller, rejecting less. But then, even then, it's rejecting a lot and then it's moving really slowly because it's small steps. And we would like to sample more efficiently. Let's change to Hamiltonian Monte Carlo. You can see that it's sometimes getting quite far away. And so when it gets this kind of the quickly other side, that's really nice. But then you can also see that sometimes it's jumping, in a way, making many evaluations but not going far away. There were a couple cases where it was practically staying at the same place. There was like this one. And then we are spending, and now again, spending a lot of evaluations and not going anywhere. In higher dimensions, this happens more often, that we would sometimes just stay in a place and the parameters Hamilton and Monte Carlo has is the step length, the step size, and how many steps. If we have short chain length, then we are closer to the Metropolice algorithm, always going only a short distance. If we have a long chain length, then we are doing sometimes many evaluations and not going anywhere. And also then the step size is related to that. If we have too large step size, let's see, we can. Okay, now we have too big step size, it's diverging. These are the green dots in my plot. It's not able to do anything sensible anymore. It's too narrow for the step size. And now Stan has the diagnostics to recognize these cases, and it can stop evaluations early. Or if we then make the step size really small, yeah, it looks smooth, but then we are doing a lot of evaluations, which is costly. So we would like to have something between. And then we want to have also nuts, which the no U-turn sampling is such that it continues building this chain until it notices that it's turning back. And you can see now that this is not exactly what's in Stan, but you can see that the chain length is anyway, it's varying. You can also make.
Turning back
So it's just we can just use the Euclidean kind of that when the distance from the point starts to get closer back. Now it's such that this decision to stop when noticing that it's turning back breaks the Markov property, and but it's possible then by carefully defining then still this how we construct, how we build up this whole chain. It's combination of kind of the doubling the length and also simulating the chain in both directions in time, and then choosing random point from the whole chain, which makes it again to obey the Markov property. But so with the nuts, it's much more easier to adapt it, and it's much more efficient than any other sampling methods, and that's why it should be also soon in GPy. We already have such an implementation which could be added. It just need to be added there. So adaptively select number of steps to improve openness and efficiency, and then there's also in the beginning step size adjustment during the initial adaptation phase, which makes it also work nicely. I have also used then in those cases where we have small number of hyperparameters and relatively kind of, I would say, moderate amount of the data, so that single GP evaluation, the marginal likelihood evaluation, with some hyperparameters takes so much time that I don't want to use MCMC for the hyperparameters. It's possible to also have a deterministic placement of integration points, and there's this central composite design where we can first find the mode, compute the Hessian at the mode. Based on the Hessian, we find eigendirections. Based on the eigendirections, we look at the also possible additional skewness. We can scale in different directions based on the skewness, and then we put points on a predicted equidensity contour, and then adjust the weights based on the true density there. Works up to 15, 20 parameters, and much faster than MCMC. And this is also now something I would recommend then to be used with like GPy-opt, that there it's likely that we don't have more than 20 hyperparameters because it was already difficult to work with more than 10-dimensional optimization. And then because it's deterministic, it's much faster than MCMC, and we don't need to look at the convergence diagnostics all the time. Of course, it can have then slightly smaller accuracy. There is now notebook. So there's the same demo I showed you with the Stan. Is also with GPy. And now comes the, it seems I'm now over time, but the optimization result from GPy, you see that it's different what I got from using Stan. And the reason here is because in both cases, Stan and GPy, we are using constraint that all these parameters have to be positive, and it's made by using log transformation. And now in GPy, that log transformation, Jacobian of that log transformation is taken into account also in optimization. In Stan, currently it's not taking the Jacobian into account when optimizing. It takes into account when sampling. And I think there should be also option that we could choose to take into account the Jacobian also when optimizing. So for this specific data realization, it turned out that the GPy were able to find actually good optimization result. But again, I've seen also cases where GPy fails. So it's really specific for this data realization. But that's currently, so we can't get the same result from GPy and Stan because of this difference in the Jacobian adjustment of that parameter transformation. And now there's examples then with the gamma priors with some weakly informative gamma prior and sampling, and even without nuts. I think I had the plots. Okay, they disappeared, the plots somehow. Let's see if they appear. Meanwhile, there's the another notebook with little bit more data, which shows nicely then this dependency between length scale and the signal variance. Okay, and let's see. Okay, it's still sampling. But since I'm over time, I'm not going now to the predictive performance estimation. But do you have questions at this point?
Aki, I had a question about your modelling of the birth rates through time.
Can you speak a little bit louder?
Sorry, I had a question about the modelling of the birth rates.
Yes.
Could you say a little bit about the kernels that you use for each one of those?
Yeah. So oh. Oops. Completely wrong folder. This one. Yeah. So there was the long length scale with the exponentiated quadratic, the kind of the short length scale, exponentiated quadratic. These are the periodic, and the periodic combined with again the exponentiated quadratic, and this was periodic with really short length scale. Was that what you wanted to know?
Well, 'cause I agree that.
And there was, and additionally, there was also kind of the indicator function for special days which are moving. Yeah.
So I agree. I completely understand that the prior is an important thing to sort out,
Mhm.
and that should definitely help this process of separating
Yes.
different timescales. But I'm also wondering about the role of the exponentiated quadratic, the RDF, in this, because essentially here, the stationary component of your model is modeling the spectrum of the detrended
Mhm.
series, and each one of your periodic components will be modeling a little subband of that spectrum.
Mhm.
So
And it's quasi-periodic.
it's quasi-periodic.
Yes, because it's the shape can change in time.
The what can change, sorry?
So
Yeah.
like in this, you can see that at different years, the shape of this weekly periodic component is changing,
Right.
so that it has limited memory.
Yes.
Yes.
But the RBF component has a very particular power spectrum.
Yes.
And the tails of that quite heavy because it's
Yes.
active, and that may cause it, if it needs to model energy in this region, it then has to push its tails out quite a
Mhm.
bit, and it'll grab other stuff, and then we'll say, oh, actually, I want to get some
Yep.
longer length scales.
Yes.
So I wonder whether there's obviously a prior issue, but there might also be an RBF issue that you need to use a lighter tailed
Yes.
kernel for the timescale variability,
Mhm.
which to just focus on particular parts of the
Yeah.
spectrum.
That's a good point. Yep. Yes.
So I mean, I missed the start, sorry. We talked a lot about identifiability. I'm always curious, I don't think identifiability is a problem. It's not the basis. I mean, it's problem algorithmically, but not modeling. I mean, should we really worry about identifiability, or does it only arise when we're looking to make a model interpretable? What do you see as the challenge of identifiability? Because it's clearly a challenge if you're non-linked.
So there's
So
a,
consider all
yeah.
solutions.
so there's two things. The weak identifiability makes computation more difficult, and then of course the other thing is the interpretability.
So is that true that it makes computation more difficult? Because actually in a lot of sampling, it makes the sampling algorithm work better.
Uh,
I mean, it depends how strongly correlated you have these things. But actually, if you've got a large, having a lot of the sampling algorithms often prefer, like the sort of circular example you have, as that gets tighter and tighter and tighter, that's when it becomes slower, right?
Yes.
As it gets wider and wider and wider, and there's less identifiability parameters. It's sort of the
but there are cases where these the non-identifiability can be such that we get really narrow things where kind of our output, the prediction stays same.
yeah, like the sum of two functions.
And then by adding some prior, we can suddenly make it, instead that it's long and narrow, it's just small,
It's true, isn't it?
concentrated.
I never know. I always worry a little bit that the prior is there to resolve the identifiability constraint. It seems like a different thing. model and it's what you, I mean, I'm going to get all Catholic about it now. The model is your model, and in practice, I'm a Protestant. The model is your model, and you should just go with it. You shouldn't be compromising your modeling choices. I don't see it separate from your modeling choices. It's all part of your modeling choices leading to a particular probabilistic model. And now you're making specific choices based around identifiability, which seems like a different criteria from making choices based around your belief structure. Unless you sort of say, I think I accept the interpretability point, unless it's all about the end, you're looking for more interpretability. We have lots of examples in modeling where people constrain their model set for interpretability.
For example, in this case, I think we had a kind of prior assumption that there are different processes going on, and we assume there's some like this seasonal effect, and in that way, I think it was sensible that we want to get them to be separated things. But then, and I've done a lot of, and so I've done a lot of these, I've done a lot of predictive models where I don't care what the length scale usually is. It doesn't matter me. It's just that do I get good predictions or not. But then there are cases where we want to get this interpretation also, which component. The automated statistician, that's kind of the problem, that there's really bad identifiability issues doing it automated. But even if it would be augmented statistician, the statistician wants interpretability out from the model.
So I think that's an interesting point. I think you want identifiability more when you're looking for interpretability. I think if you're not looking for interpretability, I don't know, maybe algorithmically it's an issue.
And then for like the Bayesian optimization, we were not really interested in interpretability. We were interested in finding the minimum with least possible amount of acquisitions. And if we know something about the process more than it's just smooth function, it helps a lot.
Aki, can I also make a comment?
Yep.
I think it's a really good message for everyone that maximum marginal likelihood is not always a rational thing to do in your application, and there are good reasons for being based about hyperparameters, like maximum likelihood in vanilla models overfits, it doesn't in the GP case. So one place where we got bitten by this was using active learning for a hearing test, and there you use a GP to model people's hearing deficits and then ask them to detect sounds or not, so you get detections or non-detections back, and you're fitting basically a GP classification model in the background. And if you're not basing about your hyperparameters, when you get very few observations at the start, your GP will collapse to a straight line and all the uncertainty will collapse away. And if you're using active learning or Bayesian type things, it then doesn't know where to choose the next point because it's collapsed out all the uncertainty. And that's because we weren't doing hyperparameter uncertainty. So I think the sorts of effects you show for regression, where things are quite bad, they're even worse for classification because the likelihood's even weaker, and you can overfit much more for fewer numbers, for larger numbers of data points, because the effect of each data point on the GP is much weaker, essentially. So yeah, definitely beware maximum marginal likelihood.
And just in case Neil didn't yet notice,
I'm getting old.
it's also over there.
That one's, a bit washed out, that one. Is that from Andrew Gelman? Is that a license?
There, I got it. With a license, you get the sticker also.
So that's Stan. I don't want to join this religion. I'm a non-frequentist. you should call them fish areas, and then just we'll just be normal, right?
And so hopefully in a few months or less than half year, the list of things I mentioned GPy doesn't have yet would be there then, so that you could do also better Bayesian inference, better Bayesian optimization with GPy.